Hi, this is Jim Janossy. We're going to talk about ASCII coding today and how simple it really is. What you're going to see in this mini lecture is tied to pages 10 and 11 of Contemporary Computing, a workbook that I wrote for a class CSC 200 at DePaul University. The URL at the bottom of this page will take you to the Amazon page where you can buy this book if you still need to. On page 10, you'll see this illustration. This illustration shows you in the vertical green column the letters forming the words hello there, with a space in between them. To the right of each letter, you see the on-off bit pattern that we've agreed upon will represent that letter when we put this information into a computer. The black dot represents a light off, and the circle represents the light on. There are 8 lights in a row. There are 8 bits in what's called a byte, or a character. So every 8 bits, grouped in this way, can form a character. But the pattern for the capital letter H we've all agreed on is off, on, off, on, off, off. In computer speak, we usually talk about the black circle, that is the current not being present, the light being off, the electrical charge not being present, as a 0. And we talk about the charge being present, or the light bulb on, as a 1. So we can conveniently express this on-off pattern in symbols that already exist. Page 11 in the workbook shows you this chart, which gives you the binary representation, that is the 0-1 pattern representation for all the common characters and uppercase letters and lowercase letters. ASCII was originally a 7-bit code. 2 to the 7th power is 128. It could represent 128 different things. That's how many different bit patterns there are. It was expanded, even in the 1960s, to 8 bits. 2 to the 8th power is 256. ASCII in its present form can represent 256 different characters or symbols. Here's the bit of that chart showing you the letters that we're going to be taking a look at. You'll be focusing on the letters that I've circled here and also attempted to highlight in yellow. Let's apply that chart to encoding these values. In fact, all I'm really going to be doing is turning the black dots into zeros and the white dots into 1s for this row. This is what the letter H would encode like in ASCII if we represented it with 0s and 1s. And it would look something like this. If you did that same thing for the letter E, that is the lowercase letter e, it would look something like this. And the letter L, the L is repeated, so the same bit pattern is repeated. And then the little letter O. Now we come to a space. What do we do with that? Just ignore it? Well, we can't. Even to transmit a space, you need a bit pattern. That is, you have to represent it somehow. And the bit pattern that you see is represented on that chart on page 11 at the bottom of the right-hand column. Notice with the capital letter H, and in the word there, the lowercase letter h, if you could carefully compare bit by bit, you'll see there's a difference, because they really are treated as different characters by the computer. Now, in reading English, we wouldn't pronounce things any differently, and we would take the same meaning. But as with passwords, there's a distinction between the uppercase and the lowercase, and that's because they really have a different bit pattern. And the difference is actually just 1 bit, as you see here. Although it's not documented on page 10, let's just dispel a little bit of confusion here about different abbreviations for binary bit patterns. At the top you see the letter H represented in 0s and 1s. That's a binary number, binary meaning 2. There are only 2 symbols in that numbering scheme. That's as high as with 1 digit you can count, 0 and 1. We have in common use a decimal number system, that is base 10, probably because we have 10 fingers, and early on people like to associate things with fingers to count them, 1, 2, 3, 4 on your fingers. Well, if you translated the base 2 number that you see at the top of the screen into a base 10 numbering system, you get a base 10 value of 72. Now, it isn't that the letter H is worth 72, that just means that the bit pattern that we associate with it, if you choose to interpret it as a binary number, it would come to the value of 72. There are other numbering systems. Number bases 8 and 16 are commonly used with computers. Since numbers like this can be confusing if you don't know the number base, sometimes in a formal way we put a subscript next to the number indicating the number base so that there is no real confusion. For example, hexadecimal base 16 would be expressed as 48, but it's not to be interpreted as a decimal 48. It actually means the same value as a decimal 72. And in the same way, an octal numbering system, base 8, which would be very relevant if you had 4 fingers on each hand, but think about this. There are some Indian tribes in North and South America that counted not using their fingers, but the spaces between the fingers. How many spaces do you have between the fingers on one hand? 4. 2 hands, you have 8. Those people would consider it very natural to have a base 8 numbering system because that's as high as they could count with their fingers, counting in that way. These are just abbreviation schemes for the string of binary values you see at the top. Early on, octal was used. Nowadays, because of the increased capacity of machines, it's much more compact to represent binary numbers in a base 16 called hexadecimal. But this is beyond our concern. I only wanted to point this out to you because various ASCII charts would talk about octal or hexadecimal. Don't be blown away by it. It's just abbreviations for bit patterns. The chart that I showed you on page 11 goes directly to bit patterns and doesn't complicate the issue with these other abbreviation schemes. Explore pages 10 and 11 in the workbook. They're going to come in handy for you for project 1.1, where I ask you to do a little more work with ASCII encoding so we make sure you understand it. The only purpose for covering this is to give you a feeling for how computers actually represent information. They can only represent things with bits on and off. So we have to translate what we understand as alphabetic symbols and number values into that kind of coding in order for computers to be able to do anything with that information. Sounds crude, but it's very powerful because many things that can store on and off patterns outside of the computer, like a CD, with a pattern of little burned-in pits burned in by a laser, very tiny into that silvery coating, that's a binary coding of much more complex information. This is what makes it possible for these machines using logic gates that can manipulate on-off values to actually handle the kind of information that we want it to handle, whether it's text information, or music encoded in bits, or video encoded in bits, or still images encoded in bits. All of these are different interpretations of the bits. When we talk about text, that is alphabetical text being expressed in bits, we're usually talking about ASCII coding. If you want more information on this, if you happen not to be enrolled in this class and the subject is interesting to you, take a look at this open course website, csc200.getclass.info, and you'll find much more information about the class and also the link to this book and to other web resources for this subject matter. And that's all I'm going to tell you now, but tune in for more of these lectures.